So if you remember back when we first started talking about derivatives, one of the first things we kind of figured out how to do was how to differentiate any polynomial. Well, in this lecture, we're going to do a very similar thing. We're going to develop some rules and some properties, and in the end, we'll be able to integrate any polynomial. Okay, so first let's start with this thing, the integral of dx. It looks like we're not integrating anything, right? But remember, there is actually a 1 in there. Right? This is the integral of 1 dx, and if we think of 1 as x to the 0 power, now we can apply our power rule. I'm going to increase the exponent by 1, divide by that new exponent, and we do a little simplifying. This is just x plus a constant. Right, so that's what the integral of dx comes out to. Okay, so I've got two properties here that we're going to use, right? And hopefully these are kind of familiar. The first one says if I have the integral of a constant times a function, I can bring that constant out in front and just integrate the function part, the part that actually has the variables we're integrating with respect to. And the second one says if I have the integral of a sum, I can split that up. That's just the sum of the individual integrals. And if you think back, we had some differentiation properties that were practically identical to these. If we have the derivative of a constant times a function, we bring that constant out in front and differentiate the function part. And similarly, the derivative of a sum, we saw several lectures back, is the sum of the individual derivatives. Okay, so let's see how we can use these. So let's take a look at this one. I want to evaluate the integral of 7x to the fourth dx. Okay, well, to do this, I'm going to start by taking that 7 and applying my first property from the previous slide, bringing it out in front of the integral. All right, so now the only part I'm actually trying to integrate is that x to the fourth, and that's a power rule situation. I'm going to increase the exponent by 1, divide by that new exponent, and I get my answer. The integral of 7x to the fourth dx is 7/5 times x to the fifth plus a constant. All right, so how about this thing? Well, here we have a general polynomial. Right? And like I said back at the beginning, now these properties and our power rule, these are going to be enough to let us integrate any polynomial. So what I'm going to do is I'm going to start by applying the second rule, and I'm going to split this up into 3 separate integrals. Then I'm going to apply the first rule. I'm going to take the 6, the -2, and the -4, bring those out in front. And now I just have 3 power rule situations. The integral of x to the third is x to the fourth over 4. The integral of x squared is x cubed over 3. And the integral of dx, that one we saw back at the very first slide here, that's just x. And now we clean up a little. We've got to reduce the fraction, right? And we get our final answer, 3/2 x to the fourth minus 2/3 x cubed minus 4x plus a constant. All right, so I've got one more for us to look at here. Now, obviously, this is not a polynomial, but we're going to apply really kind of the general process that we're going to apply to doing integrals for a little while. Now, we'll come up with some rules and some formulas and stuff down the road. But for now, finding these antiderivatives, evaluating these integrals, is really just kind of a question of looking at the thing we're integrating and saying to yourself, okay, do I know something that when I differentiate it, I get that, right? And when I see the sign, I'm thinking, okay, the sine and cosine, they kind of go back and forth, right? The derivative of sine is cosine. The derivative of the cosine, it's not the sine, it's the negative sign. So I'm going to have to add a negative, make this negative cosine of x plus a constant. So, I mean, how did I get that? It was really just kind of a question of experimentation almost that led me to that for my final answer. So in the next lecture, we're going to talk about one of those methods that I kind of referenced in passing a couple slides back. We're going to talk about something called a U substitution that's really a relatively simple tool that's going to let us expand the number of functions that we can find antiderivatives for.